Okay, we've delayed enough. All right, let's start. So, uh, part of my own research, my PhD research, is doing geospatial analysis or geoinformatics. That's what I work with under Dr. Eick in the UH DICE lab, where we end up analyzing spatial data, satellite data, data collected from aeroplanes or any kind of remote sensing data. And that kind of analysis is useful for all sorts of purposes. Like you all of you use Uber or Google Maps or Apple Maps or whatever. That's just one layer. It's used for agriculture to predict crop yields. It's used for meteorological studies to predict weather. It's used for subsidence studies to analyze how the city is settling, how population is growing, and all kinds of stuff. Most of the initial impetus for spatial analysis came from the US Department of Defense and other military organizations because it's very useful both in wartime as well as during peacetime to follow what people are doing or what other countries are doing. So that's the fundamental basis of geospatial analysis. Now, for your task three, it's a group project. I'll be giving you data and I'll be telling you what we need from you, and you're free to use any method or any system that you want to solve kind of the big picture problem that we're going to give to you. So geospatial data, like I said, is information related to the to essentially the geophysical world that we live in, right? So that includes people, business, assets, natural resources, services, infrastructure. But these are physical things. You can also calculate more abstract information as well, like how things are changing. For example, change analysis is very vital for like agricultural stuff, for understanding population movement, for understanding like all kinds of stuff. So traffic, health statistics, demographics, weather, these are more abstract, but these are also part of what geospatial analysis works with. Environmental changes, this is like an entire field of study. Ecology, sea level rise, pollution, temperature, all of this is being tracked through not just through satellite information, but also through airplanes, etc. Um, Also, some of my own research is related to emergency responders, like coordination of responses to post-natural disasters. Like, what do you do once a natural disaster has happened? How do you coordinate emergency responders? How do you coordinate the response from the government, from ordinary people, et cetera, et cetera? So, uh, even post-COVID, a lot of that information came in through like this kind of geospatial analysis. Well, you have all, Dr. Ek has been telling you how a lot of data science is conducted, what kind of data you use, how that data is stored, and et cetera, et cetera. Well, geospatial data is stored slightly differently. So, a fundamental, the most fundamental part of geospatial data is stored as vectors. So there are like 3 points. It's visible. So there are points, lines, and polygons. So this is how you represent data in a geospatial field, right? So all of these are infinitely scalable, and they don't have any defined size other than what we give it. So a point like a mathematical point, yeah, all it has is a location. Then you connect these points to create chains. Then you connect these to create polygons, and these polygons can be convex polygons, concave polygons, depending upon how you use them. Why we do it this way is because geospatial data is vast. So any data, even as simple as, for example, here on the left, the data that you see, it's just the downtown Houston road networks. You can kind of see the loop, and University of Houston would be here somewhere. So yeah, you can see the loop. But this is how geospatial data is stored because every single vertex and every single node here has a lot of metadata associated with it, right? So in any kind of geospatial analysis, you have both the physical representation of the real world that are these nodes and vertices, and then you have the information associated with it, which can be, for example, traffic levels. This is another information that is the fundamental information is stored like that, but all kinds of meta information on top of that is stored like this. So this is during Hurricane Harvey, the extent of flooding during Hurricane Harvey. So you can see that the flooding followed the riverbanks pretty much. And there are also like separate instances of flooding in other locations. So this is what I mean when I say that like the meta information and the actual geophysical information are both extremely useful for geospatial analysis. Now, I'm not going to go into too much detail about this, but vector data like this data, which is essentially a geometrical data, and this kind of information data is also called raster data. So raster data is what you see when you see, for example, your weather reports, images. Rasters are essentially images where each pixel, like instead of here, where there's no such thing as pixel level information here. These are all structures and geometry. But in raster images, every pixel contains information. What do rasters look like? So this is an example of a raster image. This is taken from the US GS satellite GOES 16, showing valley fog. So you can see as the sun rises, the fog dissipates. So this is in New England, Maine, Connecticut, that region. So you can see every single pixel in this image shows either has a particular value. So it shows either the greenery, it either shows clouds, it shows mist, and all that value is useful when you're doing geospatial analysis. Say, for example, you are doing precipitation analysis, then every pixel would give you information on how much water is contained within that, right? So, for example, like a good example is when you open Google Maps or Apple Maps. So I'll finish this up and then you can.
Yeah, sorry.
Yeah. Then you can take over. So yeah. So like I said, raster information is pixel information and not geometry, and that difference is what you'll also have to deal with, because say for example when you are trying to follow hurricanes, there are two things that you have the actual physical presence of the hurricane, which you'll see what they look like within satellite information, with the satellite data, but then you also have all other kinds of external geometric meta information. So like the pressure at the core, the direction of movement, the speed of movement, the track, where and when it was categorized. So more abstract information that like builds on top of that information. So whether it was category 1 or 2 or 3 or 4 or 5. So all that kind of information builds like, so they layer on top of each other. And depending on what kind of analysis you want to perform, you pick out one of those layers and you perform your analysis on top of that. So after this, let me give you a bunch of different examples of what like raster information on satellites of hurricanes look like. So this is Hurricane Laura. Now, this should be playing. I have no idea why these things don't play. So you can kind of see the hurricane forming and then moving across the Gulf, and then eventually here. It is so the color changes is day and night changes, and all of this was taken from the CIRA website. I'll give you a link later, so you can see you can see the entire form and then move and then just go over the Beaumont region. I think that's where Hurricane Laura hit, or was it New Orleans? Yeah, all these videos were supposed to be looping. I never understand why they sometimes don't loop. So again, so this is like, it's very difficult to analyze anything just looking at this, right? So as a day and night cycle is passing, you can look at physical information, you can guess at some things that are happening, but it's very difficult to actually do any kind of scientific analysis just by looking at it, just by looking at the eye and just by looking. So I have a bunch of other examples as well. This was Hurricane Laura. These are, wait, this is, I think, it's also a video. Yeah, this is Hurricane Beryl, which hit us a month or so. So This is much shorter. This is Hurricane Beryl just making landfall. So again, uh, this is the kind of information that you'll be given. And again, as you can see, there are some things that you can already tell from this. Like, to what extent which cities have been affected by Hurricane Beryl. Like you can see the oil fields, you can see San Antonio, Houston is right in the middle. So all of these things you can guess, and you can see the lights of Dallas on top. I think you can see New Orleans on the right. So all of these things are visible, and so what you can do with this is that you can guess, like, okay, these are the cities that were affected, these are the locations that were affected, and if I want to perform more analysis on top of that, which I'm going to show you in just a bit, these are the cities that you have to focus on. This is Milton, which just happened today. You can see the like just struck Florida yesterday. So you can see the formation, the very clear eye. It's hitting the loop current, then it's dissolving, and it's eventually. By the time this recording finished, Milton still hadn't come on shore. You can see it was just about to hit the Tampa, St. Petersburg region in the middle of Florida. So yeah. So what is your task? Like, what is your group project? Right. So you will be given a list of cities, like around we still haven't finalized the number of cities. It might be 20, it might be 25. You'll be given a list of cities that are all around this entire Gulf Coast region. Right. Yeah. From the Dutch East Indies and Cuba through Florida and the rest of the United States, like all the southern states, through Mexico and all the way to the peninsula. So in that region, from those 25 cities, and you'll be given the HURDAT, the hurricane data set, like containing information on hurricanes from all the information on hurricanes that NOAA has collected over the last 50 or so years. And you're going to perform risk analysis. You're going to tell us, okay, these are the cities that are most in danger of being hit by a hurricane. And these are the cities that are the least in danger of being hit by a hurricane. And you're going to divide this into months, essentially. So when is, say, for example, I give you New Orleans. When is New Orleans most vulnerable to hurricanes over the historical time period? So you're not doing meteorology. You're not studying the like the formation of hurricanes. You're not studying sea surface temperatures and air pressure and all kinds of other things. Not that. You're going to be doing statistical analysis, like data science analysis. So you're going to figure out, okay, based on historical patterns and historical trends, New Orleans gets hit by a hurricane in August the most, and the least in November or whatever. So, and once it's hit, and you look at information whether what type of hurricanes hits it the most. Like, do they stall over New Orleans like Harvey did over Houston? Do they get hit by Category 5s, et cetera, et cetera? So you're going to have like a bunch of specific questions, and you're going to do your best to understand them from a statistical perspective, essentially. So these are a couple of images of Hurricane Milton. So that was so one of the things I wanted to point out in the previous image, which I forgot, is that events on Earth, and specifically weather events like these are not isolated events. So as Milton was forming, there was another system that was forming of Baja California, right? So all the effects like of a hurricane, it's not just that the hurricane is affecting you. You see that smoke right up on top, on top of that image over there? That is wildfire smoke. That is wildfire smoke from the Rockies, and you can see that the smoke from the Rocky Mountain regions and from Canada, it's spreading all over the U.S. And some of that smoke, some of those particulates of the smoke, also affects weather patterns, also affects pre and post hurricane rainfall. It affects a bunch of other things, even down here in Houston, right? It affects pollen counts, it affects ozone layers, it affects like ground ozone counts, particulate counts, all sorts of other things. So again, you have to use your best judgment, because the entire weather system of Earth is there are no artificial boundaries. So everything affects everything else, right? I'll also show you a couple of other things if we have time. So one of the ways of doing what I've asked you to do is you'll be performing what's called spatial autocorrelation. So you have all correlation and causation, and these you guys all know about all of this, right? So this is a known feature of a statistical analysis. Geospatial autocorrelation works slightly differently. It takes a fundamental basis of what you know as correlation, and what it does is that there's a physical component that is added onto your standard correlation measure, right? So in geography, there's a very fundamental theorem of geography that things that are closer to each other are more similar to each other, right? And that is essentially what spatial autocorrelation tries to measure. That is whether a set of features, which is in your case, it can be a city, it can be higher temperatures, it can be lower pressures, etc., or everything that's associated with the formation and effect of a hurricane, rainfall patterns, precipitation layers, etc., and how these different data values, how these different attributes are associated to each other in space. So it's not just like correlation between two different attributes that are completely abstract, that live only in our in our brains, but we have to measure how these things correlate in actual existence, like how these things correlate on Earth. And so what spatial correlation measures is that it measures the extent to which features, essentially, like in your case, can be cities, are whether they are similar or dissimilar. So whether they're close together or whether they're disparate. So positive and negative autocorrelation means the same thing uh, as normal correlation. So uh, correlation can be measured as local or as global. So in your case, you have to figure out whether global spatial autocorrelation techniques, essentially, you don't have to build any of these, right? These are available in libraries. So you just apply a function and get a result. But you have to understand, like, whether if you're doing global spatial autocorrelation, you have to figure out whether any feature that you're trying to check, whether these couple of different things are correlated in space or not. If you do it globally, that means you are considering every single feature in the entire space. So you're considering everything in North America, and you're checking whether all kinds of different features are contributing to location being hit by a hurricane or whatever. Or you can also do local indicator spatial association. The most classic form of local autocorrelation is called LISA, which is local indicator of spatial association. So again, I'm not going to go into too much detail on this. Your simple nearest neighbor indices is also going to work. Like the very basic things that you have learned about correlation and nearest neighbor analysis and all of that also works perfectly well with geospatial data. You just have to make sure that when you are measuring correlation, you're taking into account the latitude, longitude, the location of all of these things. So. I'm going to skip over hotspot analysis because you're probably not going to be doing hotspot analysis a lot. But you can, most of this project you can do in both R and Python, because the fundamental libraries that geospatial analysis use, GDAL and GOS, are essentially written in C. So you can, both R and Python can call these GDAL libraries, and you can run your programs on top of it. I'll show you examples of what it looks like. But I changed the last part. Instead of focusing on R for today's demo, I'll show it to you in Python. One of the advantages of Python here is that because you'll be using hurricane data, HURDAT, there are certain libraries that import this data for you, and you can look at it like visualizing it and making other changes becomes much easier in Python if you're not fully within this ecosystem already. So these are the packages that you'll probably be using. GeoPandas and Raster.io and Shapely, all of them use Jidal, so you don't have to install Jidal yourself. They'll call it for you. And one other library that that I'll be showing you today is called Tropical, uh, which uh, which also relies on Jidal, but it downloads all the hurricane data for you, so that you don't have to do any of this for you. Okay, and these are the similar packages for R, which also rely on Jidal. And yeah, okay, that's it. So after this, let me move on to uh, some actual analysis. Okay, hang on. Let me give me a second so that I can mirror this screen instead of it's extend duplicate. Yes, much better, so that I can code here instead of looking back all the time and coding. Okay, so there's a couple of things. Uh, so one of the huh, it's not sharing the right screen anymore, I think. Perfect. Let me stop sharing and start sharing again. It'll probably be much easier. Okay. Hang on. Sorry, all of this is duplicate displays, not extend, it's duplicate. Is it visible? That's weird. So this is Google Earth Engine, and you can run your code over here, and it imports data for you, and it does all sorts of other things for you. So I wish I could see what I'm clicking on here, but yeah, okay. I can barely see it. So this is sea surface temperatures. So this is taken by I forgot which satellite this is taken from. I think this is taken from a Japanese satellite, and this tells you the temperature of the ocean. You see this little red spot over here. You can see that the Gulf of Mexico, this entire region is the Gulf of Mexico. I don't know if you guys can see it here. Yeah. So this is called the loop current. So this is where hotter, much warmer water from south of the equator moves into the Gulf of Mexico, and then it forms a loop, and then it flows out. Hurricanes, which wherever they form, whether they form out in the Atlantic or whether they form like Milton, whether they form lower down in the Gulf, as soon as they move over this region, they pick up energy. And so a lot of hurricanes, you'll see that as soon as they move over this region, no matter which direction they're coming from, their wind speed and their category spikes because it just picks up a lot of energy. So this is another kind of data. I'll be sharing all of this stuff with you. This is another kind of data that you'll be using. Now, the big thing that I want you guys to use is, like I said, it's called tropical. So So what Tropical does is that it takes this hurricane data set that you see here, HUD-2 data set, and then you combine it. Then you download, like, for example, in this case, I'm showing you Harvey. So we take North Atlantic, and because Harvey is from 2017, you set this to false, because if this is set to true, it'll download data from from 24 hours previous. But we don't need that data for understanding Hurricane Harvey. So we just take the North Atlantic data set, and then we keep moving. We can do individual season-based analysis. You can see here all the data of how many named hurricanes there were, how many major hurricanes there were, and all other kinds of information. But to perform your analysis, this is the data that you are going to need, right? This is like, it has a category of the hurricane, it has the names of the hurricane, it has the maximum velocity, the length of the eye, how long it started, starting latitude, longitude, ending latitude, longitude, etc., etc. So this is the kind of information that you'll be needing. Uh, there's obviously more summary information, and after that you can plot it. So this is an interesting plot because this is kind of what you're going to need for your actual analysis. So see if you can spot Harvey. Like, obviously this is let me zoom in. Man, this zoom function is so broken here. Whatever. So this is you can see this is Harvey, right? And you can see that Harvey started far, far in the middle of the Atlantic, and then it moved all the way through. It moved over the forgot the name of this peninsula, uh, the Yucatan Peninsula. Sorry, thank you. It moved over the Yucatan, and then it picked up energy. You can see that the color changed. It picked up energy over the Gulf of Mexico. Then it just made landfall over I think over Matagorda Beach, or yeah, somewhere around that, and then it stalled over there, and it stayed over there, and it dumped a lot of rainfall over Houston, flooded everything, and then it slowly moved back out over the Gulf, and then it faded out. So this is just for 2017. It's just the 2017 hurricane analysis. You can combine this. You can do 2017, 18, and 21. You all this information is also collated. You can plot everything together, and then you can see this might take slightly longer, and then you can see it's a mess. But we are not interested in what happens in the Atlantic, right? We don't really care what happens to the dolphins or the sharks or whatever. But what we care about, what your project is going to be around this region, like starting from the East Indies and Cuba, Florida, uh, Louisiana, Texas, and the Gulf Coast of Mexico. So this is what you're going to be analyzing, and we're going to give you a list of cities, and you're going to take this information, and you're going to figure out, performing statistical analysis, which of these cities are most at risk of being hit by a hurricane, and which of these cities are not at risk. To perform this kind of analysis, I'll give you lots of examples of how to use this particular library called Tropical. It's kind of a pun, I think. Yeah, you can see Tro Python py cal. It does all this kinds of analysis. So it's very good at this kind of analysis. And you can also use, say, for example, this kind of data. And this information, the satellite information, is is very up to date, but it is available from, I think, the 2020s. So if you're doing analysis even before that, the sea surface temperature data is not going to be there. And yeah, that's pretty much it. The exact details of your task is going to be up soon-ish, as soon as Dr. Eick and me we have finalized what you have to do. And other than that, yeah, that's it. I think